Hello there, and welcome to The Sleepy Scientist. If you've found your way here, chances are you're looking to drift off into a peaceful slumber, or perhaps just unwind after a long day of being gloriously human. Either way, you're in the right place. Tonight we're going to take a slow, soothing journey through time. Not the kind with wormholes and paradoxes, but the kind that happens quietly in your kitchen, your body, and the world around you. This is the chemistry of time, how molecules change, age, ripen, rust, ferment, and gently fall apart. It's the science of slow transformation and the quiet beauty of things that shift while we're not even looking. Now, I do hope this video isn't so interesting that it keeps you awake, but if it does, well, at least you'll leave with a few new facts tucked under your pillow. And who knows? Maybe you'll dream of lazy atoms and softly wilting flowers. Stranger things have happened. Before we begin, if this gentle blend of science and calm brings you any comfort, please consider tapping the like button and subscribing to the channel. It really helps. The Sleepy Scientist keep making videos like this one. Also, I'd love to know, where in the world are you listening from? And what time is it there right now? Drop it in the comments if you feel like sharing. I find it rather lovely to imagine people all across the globe curling up under the same sky listening to the same sleepy science. And just a small reminder before we begin, nothing in this video is intended as medical advice. It's simply here to soothe your curiosity, not to treat or diagnose anything at all. Now let's begin our slow descent into the chemistry of time. Rust. The word alone conjures up the image of an old bicycle left too long in the rain, or perhaps a forgotten nail on a windowsill slowly crumbling to reddish dust. But behind that flaky orange surface lies a story of chemistry that is both quiet and relentless. An invisible clock ticking away at metals, powered by nothing more than air and water. At the heart of rust is a process called oxidation. And although it sounds like something that happens inside a sci-fi reactor core, it's actually happening right now all around you, and quite possibly on your garden tools. Oxidation is a chemical reaction in which electrons are transferred from one substance to another. In the case of rusting, iron is the donor. It gives up electrons to oxygen molecules in the presence of water, and that electron loss transforms it into a new material. Iron oxide, otherwise known as rust. Now, iron by itself is a rather stable character, but when you add oxygen and a little moisture to the equation, it becomes surprisingly generous with its electrons. As those electrons drift toward oxygen, the iron atoms are oxidized, forming various types of iron oxides. These compounds have a reddish-brown color, a brittle texture, and most notably, they're far less structurally sound than the original metal. That's why bridges, ships, and buildings must constantly be monitored for rust. It's not just unsightly, it's molecular decay. But oxidation isn't just about iron. It's a broad category of reactions that includes anything from browning apples to burning wood. In fact, fire is a form of rapid oxidation. Rust, on the other hand, is oxidation in slow motion. It creeps in over months and years, like a quiet, determined sculptor carving away at civilization with a feather instead of a chisel. The interesting thing about rust is that it's both destructive and oddly poetic. Iron, once extracted from the earth as ore, refined through fire and forged into something useful, eventually begins its journey back to dust. It's the universe's way of gently undoing our work, atom by atom. There's a kind of humility in that. Even our strongest tools are on a return path to the soil. What makes rust particularly fascinating is its dependency on time. It doesn't happen in a flash like many chemical reactions. Instead, it needs repeated exposure. A humid environment accelerates it, while dry air slows it down. That's why ancient iron objects preserved in desert tombs can remain rust-free for thousands of years, while a garden spade forgotten in the rain may need replacing by next season. Scientists and archaeologists have learned to read rust like a clock. The thickness and composition of iron oxide layers on an artifact can reveal not only its age but the environment it was stored in. In shipwrecks, for example, Marine archaeologists use rust formation patterns to understand how long a vessel has been underwater and how salt water influenced the decay. Even subtle differences in the types of iron oxide present, hematite, magnetite or goethite, can offer clues about the conditions in which the rust formed. But rust isn't always an enemy. In some cases, it can actually act as a protective barrier. Certain types of steel, known as weathering steel or Corten steel, form a stable layer of rust that clings tightly to the surface and prevents deeper corrosion. This means the outer layer rusts, but the inner metal remains safe. It's counterintuitive, but in these cases, rust becomes armour. The chemistry of this protective rust relies on the composition of the alloy and the exact conditions in the atmosphere. It's a careful balance. Too much moisture or pollution, and the rust continues to flake off, exposing new layers. But under just the right circumstances, the rust becomes self-limiting. That's why architects sometimes use weathering steel for sculptures and buildings. It's functional, it's beautiful in a rustic kind of way, and it tells its own story as it ages. There's even a surprising elegance in the molecular arrangement of rust. Under a microscope, iron oxide forms intricate crystalline structures, some of them resembling delicate flowers or fractal branches. These patterns depend on the environment and the rate of oxidation. In slower, more stable conditions, the crystals can grow larger and more defined. In faster, chaotic rusting, like in salty ocean spray, they become jagged and uneven. While rust might seem like a simple process, just metal getting old, it's actually the result of a dance between electrons, water molecules and oxygen atoms choreographed over time. It's a kind of quiet performance that never stops, even when no one is watching. And unlike other chemical reactions that finish quickly and move on, rust lingers. It builds up, layer by layer, telling time not in seconds or minutes, but in stains and flakes. There's also something to be said about how rust reminds us of the interconnectedness of air, water and earth. Without moisture in the air, rust barely gets started. Without oxygen, there's no electron stealing at all, and without iron, one of the most abundant elements in Earth's crust, none of this happens. It's a trio that exists in harmony and at times in tension, a delicate balance that shapes everything from skyscrapers to fence posts. And let's not forget how oxidation affects our own bodies. Though we're not made of iron beams, we're still subject to oxidative stress. It's the same principle. Molecules in our cells lose electrons, often due to reactive oxygen species, leading to cellular damage over time. That's part of the reason we age, though thankfully we don't flake apart like rusty garden tools. At least not yet. In some respects, rust can be viewed as the physical memory of time passing. It doesn't just tell us that something is old, it shows how the elements have moved in and made themselves at home. The more rust you see, the longer the story it's been trying to tell. From abandoned factories to sunken ships, from ancient swords to forgotten wheelbarrows, rust touches everything eventually. It may take years or decades, but it always gets there. And in doing so, it teaches us a gentle truth about change, that it's constant, it's natural, and sometimes it's even beautiful. So the next time you see a rusty bolt or a weathered railing, perhaps take a moment to appreciate the chemistry behind it. Not as decay, but as transformation, an echo of the moment iron first met air and decided ever so slowly to change. Rot may not be the most glamorous of topics, but it is absolutely one of the most essential. Without decay, our world would be a cluttered museum of biological leftovers, packed with every fallen leaf, every uneaten sandwich, and every expired apple that ever existed. Fortunately, nature has a system for taking apart the old and returning it to the cycle. That system is decomposition, and it runs on chemistry. Molecules breaking down, recombining and vanishing back into the world from which they came. At its core, rot is the slow undoing of organic matter, driven by a combination of chemistry and biology. While rust works its magic on metals, rot handles the soft stuff, plants, animals, fungi and eventually us. It begins the moment life ends, when the body's cellular machinery stops running and things begin to fall apart. The protective barriers collapse, the immune system shuts down, and suddenly a whole host of microorganisms see an opportunity. Enter the microbes. Bacteria and fungi are the microscopic custodians of the natural world. While they might not wear little uniforms, they certainly know how to get things done. These tiny life forms produce enzymes, specialized proteins that accelerate chemical reactions. Enzymes are like molecular scissors, snipping apart proteins, fats, and carbohydrates into their component parts, and they do it with remarkable efficiency. Let's take an overripe banana as an example. As it softens, turns brown, and starts to give off that unmistakable scent, what you're witnessing is the coordinated effort of microbes and enzymes. The starches in the banana are broken down into simpler sugars, which explains the increasing sweetness. Meanwhile, proteins are chopped into amino acids, and lipids are dismantled into fatty acids. These new molecules are much more volatile, meaning they easily evaporate into the air, and that's what hits your nose when you lean in for a sniff. Rot isn't random. It follows a surprisingly orderly progression. The first wave of decomposition comes from the body's own enzymes, a process called autolysis. Cells begin to digest themselves from the inside out, releasing fluids and breaking open structures. It's not just dramatic, it's chemically precise. Membranes dissolve, organelles spill, and enzymes start dismantling tissues. Shortly after, bacteria that were already living inside the organism, especially in the gut, take advantage of the now defenseless environment. These microbes flourish and begin to break things down further, releasing gases such as hydrogen sulfide, methane, and ammonia. These gases are responsible for the familiar and often unpleasant odours of decay. Yes, that foul smell wafting from a compost heap or forgotten leftovers is actually a symphony of small molecules, each with its own note on the olfactory scale. Fungi also play an essential role. Moulds and mushrooms aren't just there for show, they're breaking down tougher compounds like lignin and cellulose, which are found in plant cell walls and are notoriously resistant to degradation. Fungi secrete powerful enzymes that can digest even the most stubborn bits of organic matter, helping return complex molecules back into simpler forms that can be absorbed into the soil. One of the more intriguing aspects of rot is how selective it can be. Not everything rots at the same pace, and the reasons are deeply chemical. High sugar, high water fruits like strawberries rot quickly because microbes thrive in moist, sugary environments. On the other hand, dried beans or whole grains may last months or even years without noticeable decay, because they're low in available water and contain natural defences like tannins or phytic acid. Temperature, of course, is a major player. Warm, humid environments speed up microbial activity, leading to faster decay. This is why food left out on a summer day becomes a science experiment by evening. Cold temperatures, on the other hand, slow things down dramatically. That's the entire premise behind refrigeration and freezing. It's not that decay stops entirely, but that microbes and enzymes become sluggish, like they're napping in a walk-in freezer. Oxygen levels also influence the rate and type of rot. In well-ventilated environments, aerobic bacteria dominate the scene. These are microbes that use oxygen to help break down material, often producing carbon dioxide and water. But in sealed or waterlogged spaces, like a bog or tightly wrapped plastic, you get anaerobic decomposition, which produces more methane, sulfur compounds, and other potent-smelling byproducts. Anaerobic rot tends to smell worse, look slimier, and often yields a distinctly swampy texture. Speaking of texture, one of the telltale signs of rot is softness. As cellular structures collapse and fluids are released, the tissue becomes mushy. That resistance you feel in a fresh tomato disappears as the cell walls break down, leaving behind a slippery, often gloopy mess. It's not just moisture, it's the loss of structural integrity at the microscopic level. And then there's slime. Ah yes, the universally repulsive hallmark of advanced decomposition. Slime is essentially a microbial party in full swing. As bacteria multiply, they secrete polysaccharides, long, sticky sugar molecules that form protective biofilms. These biofilms trap moisture and nutrients, creating a perfect little habitat for further decay. If you've ever picked up a forgotten cucumber and felt it dissolve in your hand, you've experienced slime in its full microbial glory. But here's the thing. As unpleasant as rot can be to our senses, it's incredibly important. Decomposition recycles nutrients back into the ecosystem. Without it, forests would be buried under leaves, oceans would brim with lifeless plankton, and compost bins would be sad and useless plastic cubes. Every molecule broken down by decay becomes part of something else. A plant root, a worm, a mushroom, or maybe even a new banana. Rot completes the cycle. There's even a kind of quiet competition happening during decomposition. Some microbes produce antibiotics to fend off rivals, others form spores to wait out tough conditions, and some specialize in very particular substances. One might be great at digesting collagen, while another prefers cellulose. This microbial ecosystem shifts over time, with different players dominating at different stages. It's like a relay race, where the baton is a rotting apple core. In forensic science, experts study the chemistry of decomposition to estimate time of death. Known as forensic taphonomy, this field examines gas emissions, temperature changes, insect activity, and even the breakdown of specific tissues to develop timelines. It's an exacting science, and one that relies heavily on understanding the chemistry behind microbial activity. And while the idea of rot may seem inherently negative, it's actually full of wonder. Some organisms rely entirely on decomposition to survive. Carrion beetles, maggots, vultures, and countless fungi live lives of quiet usefulness, making sure nothing is wasted. Even humans participate, intentionally or otherwise. We harness controlled decay in composting, food fermentation, and waste treatment. It's not destruction, it's transformation. Perhaps most impressively, rot teaches us that the end of one thing is often the beginning of another. In death, chemistry finds a way to rearrange, reassign, and reincorporate molecules into new forms, whether it's a tree trunk returning to soil or a piece of cheese growing fuzz like a tiny grey sweater. Rot is an invitation to see time not just as a linear path, but as a cycle, soft, sticky, and very much alive. There's something magical about the way a lump of dough rises, or how cabbage becomes tangy and alive with bubbles. Behind that transformation lies a quiet, slow process, powered by some of the smallest workers on Earth: yeast, bacteria, and time. This is fermentation, the art of controlled decay, and one of the most delicious collaborations between chemistry and microbes ever discovered. Fermentation is, at its heart, a form of metabolism. Microorganisms like bacteria and yeast feed on sugars and, in doing so, transform them into entirely new substances: alcohol, acids, gases, and a whole buffet of flavour compounds. It's a natural process, one that likely predates human agriculture, and yet it has been harnessed across nearly every culture on the planet. Wherever there are hungry microbes and something sweet to eat, fermentation is never far behind. Let's start with yeast, nature's microscopic alchemist. Yeast are single-celled fungi that love sugar. When you mix flour and water and let it sit, wild yeasts from the air can land on the mixture and begin to feast. In the process, they convert glucose into carbon dioxide and ethanol. Carbon dioxide makes dough puff up with tiny air pockets, while the ethanol, though mostly baked away in bread, plays a subtle role in flavour. This is alcoholic fermentation, the same basic reaction that turns grape juice into wine or barley mash into beer. It's a beautiful chemical trade-off. Sugar goes in, and in return we get bubbles, booze, and flavour. In winemaking, the choice of yeast strain, the temperature of fermentation, and even the shape of the fermentation vessel all influence the final taste. Every detail affects which molecules are created, broken down, or left untouched. In other words, time doesn't just pass, it curates. But yeast is only half the story. Bacteria also have a starring role in fermentation. Lactic acid bacteria, for example, are the powerhouses behind yogurt, sourdough bread, sauerkraut, kimchi, and dozens of other tangy treats. These microbes convert sugars into lactic acid, a compound that not only adds tartness, but also helps preserve food by lowering its pH and creating an environment where spoilage organisms can't thrive. This chemical shift is subtle but profound. In fresh milk, lactose, the milk sugar, is plentiful. As lactic acid bacteria digest it, they leave behind lactic acid, which causes the milk proteins to coagulate. That's how yogurt thickens. It's also why cheese exists at all. Add some rennet, age it properly, and you've taken a liquid and turned it into something sliceable, rich, and remarkably stable. That's the power of microbial transformation over time. Nowhere is this more evident than in fermented vegetables. Take kimchi, for instance. At first glance, it's just salted cabbage and chili paste. But over a few days or weeks, the bacteria get to work. Sugars in the cabbage are broken down, gases are released, and the flavour blossoms into something savoury, sour, and deeply satisfying. What started as a crunchy vegetable becomes a whole new experience, a dynamic mix of acids, esters, and tiny bubbles tickling your tongue. Fermentation is also a kind of preservation, an ancient refrigerator powered by chemistry instead of electricity. Long before modern canning or pasteurization, people used fermentation to keep foods edible for months or even years. That tartness you taste in pickles or sourdough is not just for flavour, it's a signal that unfriendly microbes have been pushed out, replaced by a microbial community that plays nicely with both your food and your gut. The most charming thing about fermentation is how unhurried it is. Unlike many forms of cooking which rely on heat and speed, fermentation is all about patience. You can't rush a good kimchi or a fine bottle of wine. These things take days, weeks, sometimes even years. During that time, enzymes snip apart proteins and rearrange them. Acids slowly tenderize, soften and protect. Aromatic compounds rise and fall in gentle waves, each day nudging the flavour closer to something remarkable. On a molecular level, fermentation is a chemical mosaic. Esters, for instance, are compounds that often smell fruity or floral. They're formed when acids react with alcohols, both of which are common byproducts of fermentation. That hint of banana in beer or the apple-like note in wine? You can thank esters for that. Diacetyl, which smells like butter, is another product of microbial activity. In some beers and dairy ferments, it's a welcome guest. In others, it's considered a flaw. Either way, it's a reminder that chemistry has a nose. There's also an undercurrent of cooperation in fermented foods. Many fermentations are not the work of a single organism, but of an entire microbial community. In sourdough starters, for example, wild yeasts and lactic acid bacteria live side by side, feeding on different sugars and producing different acids. Their relationship is symbiotic. Each helps maintain the balance that keeps the starter active, flavourful, and safe from invaders. It's a miniature ecosystem, right there in your mixing bowl. Cultural history is steeped in fermentation, from ancient Egyptian beer brewed in clay pots, to Chinese fermented black beans, to Ethiopian injera made with teff flour and wild microbes. Fermentation is a universal thread. These foods didn't come from laboratories. They came from trial and error, from pots left out too long, and from the realization that sometimes letting food change is better than trying to stop it. Modern science has only deepened the wonder. We now know that fermented foods can be rich in probiotics, live microbes that may benefit gut health, immune function, and even mental well-being. While not all fermented foods contain probiotics in the strictest sense, many do, and they bring with them a diversity of microbial life that's hard to replicate in a pill. But even beyond the health aspects, fermentation invites us to think differently about time. Instead of seeing it as a force that ruins freshness, fermentation asks us to see time as a collaborator. Given the right ingredients, the right microbes, and a little patience, time doesn't spoil, it improves. It deepens, mellows, and layers. Interestingly, the same microbial pathways used in food fermentation are also central to other natural processes. In soil, for instance, anaerobic bacteria perform fermentation-like reactions as they break down plant matter. In our own cells, when oxygen is scarce, certain metabolic pathways temporarily switch to anaerobic modes, producing small amounts of energy and byproducts like lactic acid. Even cheese and muscle cramps share a tiny biochemical thread. And let's not forget the sensory side. Fermented foods engage all the senses. Their textures change, from crunchy to tender, from liquid to solid. Their aromas evolve, sometimes floral, sometimes earthy, sometimes challenging. They fizz, bubble, and crackle. Each jar or batch becomes a small time capsule of change. There's something rather poetic about microbes quietly working in a dark jar on your shelf, reshaping molecules in your lunch while you go about your day. They ask for no thanks, no fanfare, just warmth, sugar, and a little time. So the next time you enjoy a slice of sourdough, a sip of kombucha, or a spoonful of yogurt, you're not just eating or drinking, you're tasting time itself. Not the kind that ticks or tocks, but the slow, molecular rhythm of life being rearranged into something new, and remarkably, wonderfully, deliciously alive. Aging is something we all experience, whether we're counting grey hairs, finding laugh lines, or wondering why our knees now make mysterious noises when we stand up. It's often viewed as a slow slide downhill, but beneath the surface, aging is really a mosaic of chemical changes. Molecules inside our bodies shift, break, unravel, and rebuild themselves, sometimes successfully, sometimes not so much. It's a kind of internal chemistry experiment that never stops, and the results, well, they're written all over our faces. Let's begin with one of the quietest culprits of aging, protein misfolding. Proteins are the workhorses of the cell, built from chains of amino acids folded into precise three-dimensional shapes. These shapes are critical. Each protein structure determines what it does, like a key fitting into a very specific molecular lock. But folding a protein isn't always straightforward. It's a bit like origami with wet spaghetti. Sometimes things go a little wrong. Misfolded proteins can lose their function, clump together, or trigger stress responses in cells. While our bodies have quality control systems to catch and refold or recycle faulty proteins, these systems aren't perfect. Over time, misfolded proteins accumulate, clogging up the cellular machinery like molecular lint in a dryer filter. In some cases, these misfolds are linked to neurodegenerative diseases like Alzheimer's or Parkinson's, where tangled proteins interfere with brain function. Even in healthy aging, though, protein damage adds up, and the cellular cleanup crew starts falling behind. Another key player in aging is oxidation, specifically oxidative stress. Our cells use oxygen to produce energy, and in the process they generate reactive oxygen species, or ROS. These are highly reactive molecules that can damage DNA, proteins, and lipids if they're not neutralized. Think of ROS as tiny chemical sparks, occasionally setting fire to important documents inside your cells. We do have antioxidants that help control them, but with age, the balance shifts. More sparks, fewer fire extinguishers. This oxidative wear and tear doesn't hit all cells equally. Some tissues, like skin and eyes, are especially vulnerable because they're more exposed to light, pollution, and other environmental stressors. Ultraviolet rays from the sun, for instance, generate ROS in skin cells, which contributes to wrinkling, sagging, and pigmentation changes. Collagen fibers, which give skin its firmness, are damaged by oxidation and start to lose their spring. The result? A face that looks more lived in over time. Hair is another canvas where time leaves its mark. The colour of our hair comes from melanin, a pigment produced by specialised cells called melanocytes. As we age, these cells slow down and eventually stop producing pigment, The exact reason isn't fully understood, but oxidative stress is once again a prime suspect. When there's too much aros in the hair follicle environment, it disrupts melanin synthesis. Without pigment, hair grows in colourless, or, as we see it, grey or white. It's not just a matter of running out of dye, it's chemistry shifting gears. Inside our cells, aging also shows up in the DNA. Every time a cell divides, it has to copy its entire genetic code. It's an astonishingly complex process that's pretty accurate, but not flawless. Over time, tiny mutations accumulate like typos in a very long book. Most of these are harmless, some are corrected, and a few can lead to problems. Accumulated DNA damage can interfere with normal cellular function, contributing to diseases of aging, including cancer. To make matters trickier, cells don't just copy DNA, they also package it. At the ends of our chromosomes are protective caps called telomeres, made of repetitive sequences that act like the plastic tips on shoelaces. These telomeres prevent chromosomes from fraying or fusing with one another. But every time a cell divides, telomeres get a little shorter. It's a natural part of the process. Eventually they become too short to protect the DNA, and the cell stops dividing or dies. This phenomenon is sometimes called the Hayflick limit, named after the scientist who discovered it. Telomeres are one of biology's more poetic clocks. The shorter they are, the closer a cell is to its last division. Cells in the skin, the immune system, and the gut, places where rapid turnover is essential, are particularly affected by telomere shortening. There are enzymes like telomerase that can rebuild telomeres, but most of our cells don't produce enough of it. Some exceptions exist, stem cells and cancer cells for instance. But in the general cellular workforce, telomeres quietly tick down like a slow countdown timer. Another area where aging chemistry becomes visible is the extracellular matrix, the complex web of proteins and sugars that supports and connects our cells. Over time, sugar molecules begin to bind irreversibly to proteins in a process called glycation. This reaction forms advanced glycation end products, or AGEs, not to be confused with actual age, though the overlap is uncanny. AGEs can stiffen tissues, reduce elasticity, and trigger inflammation. In skin, this shows up as reduced suppleness and a leathery texture. In blood vessels, it contributes to stiffness and cardiovascular risk. Muscle tissue also changes with time, not just because we use it less, but because of biochemical shifts. Mitochondria, the little energy factories inside our cells, become less efficient. They produce less energy and more aros, creating a feedback loop of damage. Meanwhile, proteins involved in muscle repair and maintenance decline. That's why building or retaining muscle becomes more challenging in older adults. It's not just lifestyle, it's molecular economics. On the immune front, aging brings a phenomenon known as immunosenescence. Immune cells gradually lose their ability to respond quickly and effectively. Some immune cells stop dividing, others become sluggish, and the result is a higher risk of infection and a less robust response to vaccines. Oxidative damage, DNA errors, and telomere shortening all contribute to this slowdown. The system that once protected us so fiercely begins to struggle, like an old guard dog with a fading bark. Even bones, often thought of as unchanging, undergo a subtle but significant chemical transformation with age. Bone is a dynamic tissue, constantly being broken down and rebuilt in response to stress and damage. As we age, the balance between breakdown and rebuilding tips. Calcium and collagen content decrease, making bones more brittle. Microfractures become harder to repair. This leads to conditions like osteoporosis, which are rooted not just in mineral loss but in changes to the molecular scaffolding of the skeleton. Amid all these transformations, it's easy to view aging as a slow collapse, but it's more accurate and more graceful to think of it as chemical unfolding. Molecules wear down, yes, but they also adapt. New bonds form, alternative pathways emerge, and life keeps going, just a bit differently. Our bodies are constantly improvising, adjusting their rhythms to the passage of time. What's especially fascinating is that some species age much more slowly than we do. The naked mole rat, for instance, shows minimal signs of aging and is remarkably resistant to cancer. Certain turtles seem to age at a glacial pace, with telomeres that don't shorten the way ours do. Even some jellyfish can revert their cells to an earlier state. These natural oddities hint that aging isn't just a universal law. It's a set of flexible biochemical rules, and evolution has been tinkering with them for eons. In humans, though, aging remains an intricate symphony of chemistry and time. It's a process shaped by both internal genetics and external influences like diet, stress, pollution, and sunlight. And while no cream or capsule can truly stop it, understanding the molecular story behind aging gives us a clearer appreciation of what's really going on inside. We're not just getting older, we're undergoing a continuous quiet transformation. Cells dividing, proteins folding, DNA replicating, bonds breaking and reforming. It's not a decay, it's a remix, a molecular evolution that plays out every second of our lives. And with each wrinkle, each silver strand of hair, and every tiny shift beneath the surface, we carry the record of time, not written in years, but etched in molecules, telling a story only chemistry can tell. There's something almost tragic about discovering a forgotten container of leftovers in the back of the fridge. What was once a proud lasagna or hearty stew has become a questionable experiment, complete with strange colours, odd textures, and a smell that suggests it's plotting revenge. This is spoilage, a natural and surprisingly complex phenomenon that turns food from nourishment into compost with the quiet power of chemistry and time. At its essence, spoilage is the breakdown of food by microbial action, enzymes, and environmental forces. It's not always dangerous. In fact, spoilage and poisoning aren't the same thing. Food can look perfectly fine and still harbour harmful bacteria, or look utterly foul and be mostly harmless. But spoilage is nature's signal that food is no longer in its prime, and the molecules within it have begun to shift in ways that we can smell, taste, and see. It starts with microbial takeover. The moment food is exposed to air, water, or human hands, it becomes a landing pad for microorganisms. Bacteria, yeasts, and moulds all eagerly await their chance to turn your snack into their new apartment. These microbes are naturally present in the environment and often harmless in small quantities, but given the right conditions, especially moisture, warmth, and time, they multiply rapidly, producing enzymes and byproducts that change the food's chemical composition. Take milk, for example. Fresh milk contains lactose, a sugar, along with proteins like casein and various fats. As lactic acid bacteria grow in the milk, they consume the lactose and convert it into lactic acid. This acid lowers the pH of the milk, which causes the casein proteins to denature and clump together. The result? Curdling. That sour smell. It comes from volatile compounds like acetic acid, butyric acid, and a suite of sulfur-containing molecules that tingle your nose in exactly the wrong way. Bread mold is another familiar villain in the spoilage saga. Mold spores are everywhere, floating invisibly through the air, clinging to surfaces, even hitching a ride on your groceries. When one of these spores lands on a moist slice of bread, it begins to germinate, sending out hyphae, thread-like structures that grow into the food, digesting starches and proteins as they go. Some molds, like penicillium, are harmless and even helpful in the making of cheese. Others, like Aspergillus flavus, can produce toxic compounds called mycotoxins. It's best not to guess which is which over breakfast. Spoilage is heavily influenced by three key factors: time, temperature, and moisture. Think of them as the spoilage triangle. Time allows chemical and biological processes to unfold. Temperature affects how quickly microbes grow. Most thrive between about 20 and 40 degrees Celsius. And moisture determines how easily these organisms can access and dissolve nutrients. Together, these elements set the stage for how fast food spoils and what kind of spoilage occurs. Dry foods like crackers and rice spoil slowly because they lack free water for microbial growth. This is why dry goods are such pantry staples. Without moisture, even the hungriest bacteria can't do much. On the flip side, foods with high water content like berries, meats or dairy spoil quickly unless refrigerated or preserved. That's because water acts as a solvent, allowing enzymes to function and bacteria to digest sugars, fats, and proteins. Refrigeration slows spoilage by lowering the temperature, which reduces microbial activity and enzyme efficiency. At around 4 degrees Celsius, most spoilage bacteria grow very slowly. Freezing takes it even further, essentially halting biological processes altogether by locking water molecules in ice crystals. This doesn't kill microbes, it just puts them on pause. Once thawed, they pick up right where they left off, which is why thawed leftovers still have a shelf life. One of the more intriguing aspects of spoilage is how it can take different forms depending on the dominant microbes. Yeast spoilage often leads to fermentation, producing carbon dioxide and alcohol. You might see bloated packaging or fizzy pickles. Bacterial spoilage can create slimy textures, strong odours, or discoloration. Mold spoilage usually presents as fuzzy growth and earthy or musty smells. Each type has its own suite of enzymes and metabolic pathways, meaning each spoils food in its own unique, flavourful way. Let's take meat for instance. When fresh, it's rich in proteins, fats, and water, a perfect microbial buffet. As spoilage begins, enzymes in the meat itself start breaking down muscle tissue, releasing peptides and amino acids. Microbes then feed on these compounds, producing foul-smelling gases like ammonia, hydrogen sulfide, and putrescine. Yes, putrescine. It smells exactly how it sounds. The texture becomes slippery as microbial colonies build biofilms and secrete extracellular substances. If your steak is shiny and smells like rotten eggs, it's time to say goodbye. Fruits and vegetables spoil in more subtle but equally impressive ways. Enzymes like polyphenol oxidase cause browning in apples and bananas, while bacterial and fungal activity breaks down cell walls, turning crisp produce into mush. Ethylene gas, a natural plant hormone, can accelerate ripening and over-ripening, especially in sensitive fruits like avocados, tomatoes, and bananas. This is why one overripe banana can turn the whole fruit bowl into a compost heap in record time. Thankfully, humans are nothing if not inventive. We've developed a variety of methods to delay or prevent spoilage, many of which revolve around changing the chemical environment of food. Chemical preservatives, for example, are substances added to slow down microbial growth or enzymatic reactions. Common examples include sodium benzoate, potassium sorbate, and calcium propionate. These compounds interfere with microbial metabolism, often by altering pH or disrupting cell membranes. Salt and sugar are two of the oldest preservatives around. In high concentrations, they draw water out of microbial cells through osmosis, dehydrating and killing them. That's why salted meats and jams last so long. Microbes simply can't thrive in such a dry environment, even if the food itself feels moist to us. Vinegar works similarly by creating an acidic environment hostile to most bacteria. That sharp, tangy brine in pickles isn't just for flavour, it's a chemical moat, keeping the microbial invaders at bay. Another approach is vacuum sealing or modified atmosphere packaging. These methods remove or replace the oxygen inside packaging, limiting the growth of aerobic microbes, the ones that need oxygen to survive. In the absence of oxygen, many spoilage organisms are unable to grow. It's not foolproof, though. Some anaerobic bacteria, like Clostridium botulinum, actually thrive in oxygen-free environments, which is why food safety standards still require heat treatment and acidity controls. Pasteurization is yet another powerful technique. Named after Louis Pasteur, it involves heating food to a specific temperature for a set time to kill harmful microbes. Milk, juices, and canned goods all undergo pasteurization to extend shelf life and ensure safety. The The key is to kill the bad guys without ruining the food's flavour or texture. It's a delicate dance of time and temperature, a bit like cooking, but more precise. Spoilage also helps us think about time in a uniquely sensory way. We don't just measure freshness by date stamped on packaging. We feel it in textures, see it in colours, and smell it the moment we open a container. Our senses are surprisingly well tuned to chemical changes. Humans have evolved to detect the volatile compounds produced by microbial metabolism, particularly those associated with danger. That sour milk smell or green fuzz on bread is your nose's way of saying, perhaps not today. Of course, not all signs of spoilage are dramatic. Sometimes it's just a change in flavour or a loss of crispness. These subtle shifts are still the result of molecular transformations, invisible yet undeniable. Over time, even well-preserved foods lose their peak character. Fats go rancid, flavours dull, vitamins degrade. It's all chemistry, marching steadily forward. What's remarkable is how universal the process of spoilage is. Whether it's a sandwich in your lunchbox, a peach in an orchard, or a preserved relic in an archaeological dig, all organic matter is subject to the same principles: exposure, breakdown, and change. Spoilage reminds us that food is not static. It's dynamic, living even after harvest, and constantly interacting with the world around it. Understanding this makes us not just better consumers, but more appreciative ones. That perfect apple you bite into is a snapshot in time, a balance between ripeness and decline, freshness and transformation. And when it finally turns soft or speckled or sour, it's not failing. It's just continuing its chemical journey, one molecule at a time. There's something mesmerizing about watching a fire. The crackling of wood, the dance of orange flames, the soft collapse of embers into ash. It's one of the oldest and most hypnotic phenomena known to humans. Long before we understood atoms or molecules, we understood fire, or at least we thought we did. It cooked our food, kept us warm, scared off predators, and gave us light in the darkness. But at its core, fire is chemistry, specifically the fast-paced high-energy drama of oxidation. Combustion is what happens when a material reacts quickly with oxygen, releasing heat and light. In most cases, this reaction involves carbon-based compounds, like the cellulose in wood or the hydrocarbons in wax. When you strike a match or light a candle, you're initiating a rapid series of reactions where electrons leap, bonds break, and new molecules form in a flurry of excited activity. It's oxidation on caffeine, loud, bright, and hot. But not all fire burns at the same tempo. Some flames rage and roar while others smoulder like they're savouring every moment. Fast combustion is what you see in a roaring bonfire. Oxygen rushes in, molecules collide at high speeds, and the fuel is rapidly converted into heat, carbon dioxide, and water vapour. This type of burn is flashy but short-lived. It consumes its fuel quickly, leaving behind a trail of ash and soot. Then there's smouldering, a slower, cooler form of combustion. When oxygen is limited, or when the material is dense and packed tightly, the fire takes its time. Instead of leaping flames, you get glowing embers, soft wisps of smoke, and a gentle heat that can linger for hours. It's still oxidation, just in slow motion. In fact, smouldering fires can be surprisingly persistent. Peat fires in marshy ground, for example, can burn underground for weeks or even months, flaring up when they reach a pocket of dry material. Some coal seam fires around the world have been burning for decades. One in Australia is thought to have been smouldering quietly for over 6,000 years. When you burn wood, you're not just watching it disappear, you're witnessing a sequence of transformations. Wood is made primarily of cellulose, hemicellulose, and lignin, complex polymers that give trees their strength. As the temperature rises, these polymers begin to break apart. First, the moisture is driven off. Then the long carbohydrate chains begin to unravel in a process called pyrolysis. This is the thermal decomposition of organic material in the absence of oxygen. It doesn't combust right away. It just starts to crack and smoke. The smoke you see rising from burning wood is full of volatile organic compounds, tiny fragments of broken molecules that didn't fully oxidize. These compounds can ignite in the presence of a flame, which is why a smoking log can suddenly burst back into fire when poked or repositioned. That rush of flame is the volatile gases finally getting their chance to react with oxygen and join the combustion party. Ash, on the other hand, is what's left behind when almost everything else is gone. It's the mineral skeleton of the wood, the calcium, potassium, magnesium and other inorganic elements that didn't burn. Ash has its own charm. In small amounts, it's used to make soap, fertilize soil, and in traditional glass making. Chemically speaking, ash is the stable residue of combustion, immune to fire because it's already oxidized as much as it possibly can be. Then there's charcoal, that black brittle substance that feels like fossilized smoke. Charcoal is created when wood is heated in a low oxygen environment, allowing pyrolysis to occur without full combustion. The volatile compounds are driven off, and what remains is mostly carbon. Charcoal burns more cleanly and at a higher temperature than wood, making it ideal for cooking and metalworking. Ancient blacksmiths and modern backyard grill masters both rely on its slow, steady heat. Charcoal also represents a kind of chemical pause. It's wood that was halfway to becoming ash but took a detour. Because it's mostly carbon, it doesn't rot easily, and it can persist in soil for hundreds or even thousands of years. In fact, biochar, a form of charcoal used as a soil amendment, has been found in Amazonian soil dating back centuries. Its presence not only improves soil fertility, but also locks away carbon, making it a fascinating tool for sustainable agriculture. Let's not overlook the beauty of embers. Those glowing red coals aren't just pretty, they're the visible sign of heat being radiated from hot carbon and mineral surfaces. As electrons in the atoms are jostled by thermal energy, they jump to higher energy states and fall back again, releasing photons of visible light. The colour of those photons gives us clues about temperature. Dull red embers are cooler than bright orange or white-hot coals. It's a natural thermometer glowing right before your eyes. The rate at which a fire releases energy is influenced by a variety of factors: oxygen availability, fuel size and shape, moisture content, and temperature. Dry splintered wood burns quickly and cleanly. A damp log, not so much. It'll smoulder, hiss, and produce more smoke than flame. Moisture acts like a chemical speed bump, absorbing energy as it evaporates and slowing down the reaction. Interestingly, the smoke itself is full of complex chemistry. It's not just leftover fuel. It contains carbon monoxide, formaldehyde, benzene, and dozens of other compounds. That's why campfires smell the way they do, and also why proper ventilation is essential when burning anything indoors. Even the soot particles or black carbon are chemically reactive and can affect both health and climate when they rise into the atmosphere. Fire, in this sense, is both a transformation and a performance. It takes solid, stable matter and converts it into heat, gas, light, and ash. It's a dramatic display of molecules breaking and reforming at high speed, and yet when the flames die down and only the embers remain, you're left with something more meditative. A slow burn, a lingering warmth, a memory of energy released. This contrast between fire's rapid ignition and its slow smoulder mirrors the many ways time shapes chemical change. Fast reactions capture our attention. They explode, glow, or vanish in seconds. But slow reactions, like the transition from log to ember to ash, are just as meaningful. They leave behind traces, textures, and materials that tell a deeper story. In those smouldering remains is the fingerprint of time. Combustion also reminds us that energy is never truly lost. The heat released from a fire once resided in the bonds of cellulose and lignin, energy captured from sunlight through photosynthesis. When the wood burns, that stored solar energy is released back into the environment. In a way, warming your hands by a campfire is like borrowing heat from the sun's past generosity. It's a full circle moment, facilitated by oxidation. So the next time you see a fire winding down, don't just see the end of something, see the continuation of a chemical journey. The glowing coals, the drifting smoke, the soft crumble of ash under your fingers. They're all remnants of reactions shaped by time, temperature, and transformation. Fire may burn fast, but it also lingers long after the flames go out in the molecules it leaves behind. In the intricate clockwork of life, there's a cast of microscopic characters working tirelessly to keep things moving. Their job? To make chemical reactions happen faster, more efficiently, and often with breathtaking precision. These unsung heroes are enzymes, biological catalysts that ensure the chemistry of life keeps pace with, well, life itself. Without them, you'd still be trying to digest last Tuesday's lunch. At their core, enzymes are proteins, very special proteins. They're folded into shapes so specific, so finely tuned, that they can recognize and bind to exact molecules, called substrates, and transform them into something new. Imagine a key that not only fits a lock but also helps rearrange the entire room behind the door, all without needing to be replaced. That's an enzyme in action. Reactions that might take weeks, years, or even centuries to occur spontaneously in a lab can happen in mere seconds inside a living cell thanks to enzymes. They work by lowering the activation energy required to start a chemical reaction. Think of it like reducing the height of a hill you need to climb. Suddenly, even sluggish molecules can make the trip. One of the most visible and oddly relatable examples of enzyme action is the humble banana turning brown. This change is due to enzymatic browning, a process catalyzed by an enzyme called polyphenol oxidase. When a banana is bruised or begins to overripen, cell structures break down, allowing the enzyme to interact with phenolic compounds in the fruit. In the presence of oxygen, these compounds are oxidized into melanin-like pigments, producing that familiar brown color. This browning doesn't just happen in bananas, it affects apples, avocados, and potatoes too. It's why chefs sometimes dunk sliced fruit into lemon juice. The acidity helps denature the enzymes or slows down their activity, buying a bit more time before the transformation begins. It's a tiny chemical intervention in the race against ripening. Enzymes are everywhere, doing everything. In your mouth, amylase starts breaking down starches into sugars before you even swallow. In your stomach, pepsin digests proteins into peptides. In your liver, enzymes help detoxify chemicals, converting potentially harmful compounds into something your body can safely process or eliminate. Every blink, breath, and heartbeat is coordinated by enzymes speeding up the essential reactions of life. One particularly fascinating feature of enzymes is their specificity. Many of them recognize just one substrate, or a narrow group of related molecules. This specificity ensures that cellular chemistry doesn't descend into chaos. It's a bit like a carefully managed assembly line. Each enzyme has a dedicated station, a specific role, and a clear product. This tight control allows cells to perform remarkable feats of regulation. Enzyme activity can be switched on or off in response to changes in the environment, such as temperature, pH, or the presence of certain molecules. It's how your body knows to increase digestive enzyme production when you eat, or to produce more repair enzymes when you're injured. It's a chemical response system with split-second timing. But as precise as they are, enzymes are also surprisingly fragile. Changes in temperature, pH, or the presence of inhibitors can reduce their efficiency or shut them down entirely. Heat can cause enzymes to denature, meaning their carefully folded structures unravel, leaving them useless. That's why high fevers are dangerous, not just because they make you feel awful, but because they can impair enzyme function throughout the body. Enzymes don't just accelerate reactions, they also play a role in managing time within the cell. Some act as molecular clocks, regulating processes that must happen in a specific order. For example, in the cell cycle, the tightly choreographed process of growth and division, enzymes known as kinases control when a cell progresses from one phase to the next. If these enzymes are disrupted or become overactive, the result can be uncontrolled growth or cancer. On a longer timescale, the efficiency of enzymes gradually changes as we age. Just like people, enzymes can slow down, make more mistakes, or become less responsive. Enzymes involved in DNA repair, for instance, become less effective over time, allowing mutations to accumulate. Others involved in metabolic regulation may become overworked or overwhelmed, contributing to age-related conditions like insulin resistance, inflammation, or neurodegeneration. In some diseases, enzyme malfunction is at the very heart of the problem. For example, in phenylketonuria, a rare genetic disorder, a missing enzyme prevents the proper breakdown of the amino acid phenylalanine. Without this enzyme, phenylalanine builds up in the body and can cause brain damage if left untreated. In Tay-Sachs disease, another genetic condition, a missing enzyme leads to the accumulation of fatty substances in the brain with devastating effects. Even common conditions like lactose intolerance boil down to enzymes, or the lack thereof. In this case, it's lactase, the enzyme that breaks down lactose, the sugar in milk. Many people produce plenty of lactose in infancy but lose the ability as they age. The result? A dramatic reminder that chemistry and digestion are closely linked, often at inconvenient moments. Scientists have found ingenious ways to use enzymes outside the body too. In the food industry, enzymes clarify fruit juice, tenderize meat, and even make cheese. In laundry detergents, enzymes help break down stains. Protein-eating proteases, fat-targeting lipases, and starch-loving amylases all work together to scrub your socks clean. Enzymes are even used in forensic science to amplify DNA samples for identification, thanks to a heat-tolerant enzyme discovered in bacteria from hot springs. In medicine, enzyme therapies are being developed to replace faulty or missing enzymes, especially in genetic disorders. Some cancer treatments involve targeting the enzymes that tumours rely on for rapid growth, and in biotechnology, synthetic enzymes are being engineered to perform new tasks, from breaking down plastic to fixing carbon dioxide into useful compounds. It's enzyme innovation on a global scale. One of the great advantages of enzymes is their efficiency. They can convert thousands of substrate molecules per second, often without generating toxic byproducts. And because they're biodegradable and highly specific, they're an environmentally friendly alternative to many industrial catalysts. This makes them valuable not just in science, but in sustainability. What makes enzymes truly enchanting is that they embody the intersection of structure and function. Their activity depends entirely on their shape, a delicate three-dimensional form held together by hydrogen bonds, ionic interactions, and hydrophobic pockets. It's this structural choreography that allows them to cradle a molecule, coax it into reacting, and then release the result, ready to start again. But enzymes don't last forever. Over time, they can become damaged by oxidation, inhibited by other molecules, or simply wear out. Some enzymes get recycled and rebuilt, others are broken down and replaced. It's a constant balance, a quiet background hum of activity that allows life to carry on moment to moment. Enzymes, in a very real sense, are the reason time moves at a biologically useful speed. Without them, life's chemistry would unfold far too slowly to be practical. Your breakfast would take hours to digest, your muscles would twitch sluggishly, and your thoughts, well, they might take a while to arrive. So the next time you watch a banana slowly brown on the countertop, or feel a pang of hunger stir your stomach into action, know that enzymes are quietly at work, measuring time not with ticks or tocks, but with molecular transformations that happen faster than you can blink. They are the caretakers of pace in a world made of change. And in the great story of time and molecules, enzymes are the editors, keeping everything running on schedule. There's something oddly comforting about opening the freezer and seeing it packed with neatly labelled meals, frozen peas, and maybe, if you're lucky, a forgotten tub of ice cream. It's a little portal of suspended time, a frosty archive where food and flavour are paused, sometimes for weeks or months. Freezing is our most reliable weapon in the age-old battle against spoilage, rot, and molecular mischief. It doesn't stop time exactly, but it slows the clock just enough to make a difference. At the heart of freezing's effectiveness is a very simple truth. Temperature controls molecular motion. When things are warm, molecules bounce around energetically, colliding with each other, reacting, transforming, and generally causing chemical chaos. But as the temperature drops, that activity slows. Molecules lose energy, vibrations decrease, and reactions start to drag. Eventually, at sufficiently low temperatures, molecular motion becomes so sluggish that most biological and chemical processes grind to a near halt. Water, the universal solvent of life, plays a starring role in all this. In its liquid state, it's constantly helping things dissolve, move, and react. But when frozen, water forms a crystalline lattice, ice. This structure locks molecules in place, traps microbes in stasis, and deprives enzymes of the liquid environment they need to function. No water, no wiggling molecules, no mischief. This is why freezing food works so well. By reducing the temperature and solidifying the water inside, you're essentially pressing pause on both spoilage microbes and the chemical reactions that cause deterioration. Bacteria stop multiplying, enzymes stop snipping, flavours stop fading. It's not a perfect preservation method, but it's incredibly effective for most everyday needs. Of course, freezing isn't just about shoving things in the icebox and hoping for the best. The way something is frozen affects its texture, flavour, and longevity. Slow freezing, which happens when a large piece of food is cooled gradually, causes water to form large ice crystals. These can rupture cell walls and lead to mushy textures once thawed. Think of a strawberry that's gone soft and soggy after a stint in the freezer. That's ice doing a bit of unintentional damage. Fast freezing, on the other hand, creates smaller crystals and preserves texture more effectively. This principle is behind flash freezing, a technique used in food processing to lock in freshness while minimizing damage. Fish, vegetables, and even pre-cooked meals benefit from rapid cooling that keeps their microscopic architecture intact. The goal is to get cold quickly, so molecules don't have time to rearrange into troublemaking forms. And then there's freeze-drying, an elegant blend of freezing and vacuum wizardry that removes water from food without passing through the liquid phase. The process begins by freezing the food solid, then reducing the surrounding pressure so that the ice sublimates. That is, it skips the melting stage and turns directly into vapour. What's left is a porous, dry structure that retains much of the original flavour and shape, but is now shelf-stable. Freeze-dried strawberries, for example, crunch in your mouth like candy, yet regain much of their original character when rehydrated. Astronauts snack on freeze-dried meals in space, not because it's trendy, but because those foods are light, safe and stable without refrigeration. The same technique is used for preserving pharmaceuticals, sensitive biological samples, and, increasingly, whole organisms for long-term storage. This brings us to cryogenics, the study of extremely low temperatures and how materials behave under such conditions. In the biological world, cryopreservation is the art of storing cells, tissues, or even entire embryos in liquid nitrogen, which hovers at around -196 degrees Celsius. At that temperature, nearly all molecular motion stops. Cells are preserved in a kind of suspended animation, waiting to be thawed and brought back to life. Sperm, eggs, stem cells, and even certain organs have all been successfully frozen and revived for medical use. The trick is avoiding ice crystal formation, which can destroy delicate structures. Cryoprotectants, chemicals like glycerol or dimethyl sulfoxide, are used to prevent ice damage, essentially shielding cells during the freezing process. It's a delicate balancing act between preservation and destruction, and scientists continue to refine the techniques. In more speculative territory, There are people who've opted to have their entire bodies frozen after death, in the hope that future medicine might one day revive them. This is whole-body cryonics. Whether or not such revival is ever possible remains deeply uncertain. The damage done during freezing, particularly at the level of brain tissue and cellular membranes, is still formidable. But as an idea, it reflects something profound, a desire to outwit time through chemistry. Even outside the lab, freezing has transformed how we live. It has changed global trade, made seasonal food available year-round, and reduced food waste on an astonishing scale. Ice cream lovers owe their cravings to early breakthroughs in freezing technology, including the invention of mechanical refrigeration in the 19th century and Clarence Birdseye's pioneering work in flash freezing in the 1920s. But no matter how cold it gets, nothing is truly timeless. Freezing slows reactions, but it doesn't stop them entirely. Over very long periods, chemical changes can still occur in frozen materials. Lipids can oxidize, leading to freezer burn, a term that sounds dramatic but really just refers to dehydration and lipid oxidation that affect texture and flavor. Proteins can denature, vitamins can degrade. Even in deep freeze, time whispers to the molecules, nudging them ever so gently toward change. In ancient permafrost, scientists have discovered frozen animals, mammoths, wolves, and even bacteria, preserved for tens of thousands of years. These frozen time capsules reveal not just the biology of the past, but the limitations of preservation. Tissues may look pristine, but on the molecular level, degradation has already begun. The information encoded in DNA begins to fray. Ice does not grant immortality, it merely slows the fade. Drying is another preservation method that chases the same goal, slowing time by removing water. Without moisture, enzymes and microbes cannot function. Traditional drying, like sun-drying fruits or air-curing meats, has been used for millennia. Modern methods use heat, airflow, and even microwaves to accelerate the process, but the principle is the same. Remove water, preserve structure, delay decay. Dehydrated foods may look shriveled, but their chemistry is remarkably stable. Raisins, jerky, and powdered milk can last for months or even years. Some dried spices like peppercorns or cinnamon sticks remain aromatic for astonishingly long periods. They're volatile oils protected by structure and dryness. Dried beans and rice, properly stored, can outlast most pantry companions. Still, drying comes with trade-offs. Flavour can concentrate or fade, colours may darken, and texture becomes, well, dry. Rehydration can bring some of it back, but not all. It's a bit like pressing pause, but knowing that when you hit play again, the scene may be a little different. Freezing and drying are our best attempts to hold on, to moments, to meals, to the delicate balance of molecules before time takes over. They reflect our desire to resist impermanence, to keep things just as they are for a little while longer, and though they don't offer forever, they offer enough time to enjoy, to share, to remember. Because in the end, even the most perfectly frozen strawberry or expertly dried herb is still part of time's long story. The molecules may pause, the reactions may stall, but the moment continues to drift. Ice melts, air returns, and the chemistry of change resumes its quiet, patient work. Not everything ages with the same obvious flair as ripening bananas or rusting iron. Some things seem to resist time altogether, standing still while the world moves on. Crystals are among those quiet rebels. Whether it's a diamond locked in a ring, a grain of salt clinging to your pretzel, or a glittering geode cracked open to reveal a kaleidoscope of facets, crystals give the impression of absolute permanence. But look closer, much, much closer, and you'll find a story of patience, structure, and time told through atoms arranged with extraordinary order. At its most basic, a crystal is a solid material whose atoms are arranged in a repeating, orderly pattern. This structure gives crystals their unique shapes, strength, and, often, their beauty. But that tidy arrangement also plays a big role in how crystals interact with time. The reason many crystalline materials seem unchanging isn't because they defy chemistry. It's because their internal order makes them chemically and physically stable. Time moves through them like a whisper rather than a shout. Take diamonds, for instance. They're made entirely of carbon atoms, the same element that forms graphite, charcoal, and even the gooey centre of some squishy candies. What makes a diamond different is how those carbon atoms are arranged. In diamonds, each carbon is bonded to 4 others in a 3-dimensional network that is exceptionally tight and strong. This rigid structure doesn't give molecules much room to move around or react. As a result, diamonds don't degrade easily. They don't rot, melt under everyday conditions, or dissolve in water. They just sit there, sparkling with centuries of stillness. Diamonds are also incredibly old. Many were formed over 1 billion years ago, deep in the Earth's mantle under immense pressure and heat. They travelled to the surface through volcanic eruptions and have been sitting in the crust ever since, mostly unchanged. In fact, if you're wearing a diamond, you're probably wearing something older than the continents themselves. It's not just jewellery, it's geologic history with a good marketing team. Salt crystals tell a slightly different story but share the same principles. Table salt, or sodium chloride, forms cubic crystals that are almost geometric perfection. Unlike diamonds, salt is quite soluble. It dissolves easily in water, but in its solid, dry form it's incredibly stable. That box of salt in your pantry, it'll outlive your cereal, your spices, and probably your Tupperware. The ordered lattice of alternating sodium and chloride ions holds steady, resisting the chaos that time typically brings. What makes crystals so enduring is their strong repetitive bonding. In many cases, this bonding requires a significant input of energy to disrupt. Heat, moisture, or chemical attack is needed to break apart a crystal structure. Without those external nudges, many crystals will happily remain in their current state for thousands, or even millions of years. Their atoms aren't in a hurry, and time has to work very hard to get a word in. But just because something appears unchanged doesn't mean it's motionless. Even within crystals, atoms are vibrating. These vibrations increase with temperature, and under the right conditions they can lead to change. In some minerals, atoms very slowly rearrange themselves, a process known as solid-state diffusion. It's incredibly slow, measured in micrometers per million years, but it does happen. Over vast spans of time, this can subtly alter the composition of crystals, changing their colour, clarity, or internal structure. This is one of the reasons geologists are so fascinated by crystals. They act as time capsules, preserving not only their own chemistry, but also clues about the environment in which they formed. The shape, size, and internal zoning of a crystal can reveal the temperature, pressure, and chemical makeup of the rock around it when it grew. Some crystals contain fluid inclusions, tiny pockets of liquid trapped during formation, that provide direct samples of ancient Earth chemistry. The formation of crystals itself is a masterclass in the chemistry of slowness. Crystals grow from a fluid, either a melt, a vapour, or a solution, as atoms or molecules slowly arrange themselves into a repeating pattern. This process can take minutes or millennia, depending on the environment. In lava cooling at the Earth's surface, crystals form quickly and may be small and imperfect. In deep underground caverns, crystals can grow over thousands of years into massive shimmering structures. One of the most jaw-dropping examples of this slow crystallization comes from the Cave of the Crystals in Naka, Mexico. There, beneath the Earth's surface, conditions of high humidity, stable temperature, and mineral-rich water allowed selenite crystals to grow to astonishing sizes, some over 30 feet long. These behemoths took hundreds of thousands of years to reach their size, growing slowly and steadily in a quiet underground cathedral of chemistry. Even everyday crystals hint at the passage of time. Snowflakes, for example, form when water vapour condenses and freezes around a tiny particle in the atmosphere. The temperature and humidity at the time of formation influence their shape, creating a stunning variety of six-sided symmetry. While each snowflake is short-lived, Its form tells a brief story of temperature, vapor pressure, and the molecular dance of water molecules settling into place. Not all crystals are stable forever though. Some undergo what's called phase transitions. Under the right conditions, heat, pressure, or exposure to different chemicals, a crystal can rearrange its atoms into a new structure. This is what happens when graphite turns into diamond under high pressure, or when minerals change during metamorphism. In these cases, stability isn't lost, it's transformed. The atoms still follow the rules of crystal formation, but those rules shift with the environment. There's a strange paradox at play here. Crystals give the illusion of permanence, but they're really just very slow players in the broader chemical theatre. Their resistance to change isn't absolute, it's conditional. With the right nudge, even the most ancient crystal can be coaxed into change. But in the absence of those nudges, they offer a kind of chemical serenity, a refusal to be hurried by time. This long view of chemical stability also has practical benefits. Crystals are used as timekeepers, quite literally. Quartz crystals, when subjected to an electric field, vibrate at a precise frequency. This property, known as piezoelectricity, is what makes quartz useful in watches, clocks, and electronic devices. The vibrations of a quartz crystal can be counted to mark seconds, minutes, and hours, giving us an extremely accurate way to measure time using something that seems almost immune to it. In another application, the regularity of crystal structures makes them ideal for optics and electronics. Silicon, the backbone of computer chips, is a crystalline material that allows precise control over electrical flow. The orderly arrangement of atoms lets scientists design circuits at the nanometer scale. In this way, the very structure that resists change also enables some of the most advanced technology we have. What crystals remind us is that time isn't always about movement or decay. Sometimes it's about stillness, about the spaces where change slows to a crawl and form holds steady. In a world filled with shifting tides and transforming matter, crystals offer a kind of quiet defiance. Their atoms are arranged not in chaos but in harmony, each one locked into place, whispering the same arrangement to the next. So when you look at a grain of salt, a diamond, or even the sugar in your tea, you're not just seeing a substance, you're witnessing a moment of balance, a structure that for now holds, its chemistry taking its time, and reminding us that sometimes stillness is the most elegant form of endurance. Scent is one of the most fleeting yet powerful experiences we encounter. A single whiff can transport you back years, stir emotions you thought were long gone, or conjure up vivid images of places you haven't visited in decades. But behind this invisible magic lies chemistry, specifically the movement and transformation of volatile molecules in air over time. Smell is time-bound. It's a story told in molecules that rise, drift, change, and eventually vanish. Let's begin with a flower. Freshly bloomed, it might release a rich bouquet of fragrant compounds, floral, citrusy, perhaps a little spicy. But wait a few days, and that scent fades. The petals wilt, the fragrance dulls, and the vibrant chemical message it once broadcasted is no longer detectable. What happened? The answer lies in volatility. The molecules responsible for scent are quite literally fleeting. Volatile organic compounds, known as VOCs, are small, lightweight molecules that evaporate easily. That's what makes them perfect for olfaction. They lift off from a surface and waft through the air, where they can travel into your nose and interact with olfactory receptors. These molecules are usually rich in elements like carbon, hydrogen, and oxygen, and often contain functional groups such as aldehydes, esters, alcohols, and ketones. Flowers produce these compounds to attract pollinators. Bees, butterflies, and other insects are exquisitely sensitive to scent. The chemical messages released by blossoms signal ripeness, fertility, and food. But those compounds don't stick around forever. Exposure to sunlight, oxygen, and microbial activity can break them down. Some oxidize into less aromatic forms, while others degrade into entirely different molecules. The bloom doesn't just fade visually, it fades chemically. Perfumes follow a similar story, albeit with a little more human orchestration. A fine perfume is a carefully layered blend of volatile molecules designed to unfold over time. It typically consists of 3 layers: top notes, middle notes, and base notes. Top notes are the most volatile, fresh, bright, and fleeting. Citrus, herbs, and light florals often live here. They hit your nose first and evaporate quickly, sometimes within minutes. Middle notes, or heart notes, develop as the top notes fade. These are often more robust and last longer. Think of spices, florals like jasmine or rose, and green aromas. Finally, base notes are the slowest to evaporate. These molecules are larger and less volatile, providing the lasting impression of the fragrance. Woody, musky, or resinous compounds often anchor the perfume, lingering for hours or even days. Over time, a perfume evolves on the skin as its components evaporate at different rates. It's not just a single scent, it's a chemical journey. Environmental conditions like temperature, humidity, and even your skin's pH can influence how a fragrance develops. That's why the same perfume can smell different on 2 people, or even on the same person in summer versus winter. But even bottled and stored, perfumes aren't immune to time. They degrade slowly through oxidation, light exposure, and interaction with air in the bottle's headspace. A once vibrant floral scent might take on a sharper, more acidic edge. Vanilla might deepen into something smokier, and some of the original brightness may simply fade away, not because the perfume is bad, but because its most volatile players have left the stage. The chemistry of smell doesn't stop at flowers and perfume. Everything around us emits volatile compounds to some extent. A fresh orange, a cup of coffee, new books, old wood, rain on dry soil. All of these smells are carried by specific molecules. Petrichor, the smell of rain on dry earth, comes largely from a compound called geosmin, which is produced by soil-dwelling bacteria. That unmistakable new car smell, a mixture of VOCs off-gassed from synthetic materials like plastic, adhesives, and upholstery treatments. And yes, even decay has a distinct scent profile. As organic matter breaks down, it releases a range of molecules like cadaverine, putrescine, ammonia, and sulfur compounds. These smells are, understandably, off-putting. Our aversion to them is an evolutionary adaptation, guiding us away from spoiled or dangerous substances. What's fascinating is how our brains respond to scent. Unlike other senses, the olfactory system has a direct line to the brain's limbic system, where emotion and memory reside. That's why smells can feel emotionally loaded, and why they can spark memories with a vividness no photograph can match. You might forget the details of a childhood birthday party, but the smell of birthday cake, or even the faint aroma of matches and balloons, might bring it all rushing back. This emotional connection gives smell a kind of timeless quality in our perception, even though the molecules themselves are anything but timeless. They are in constant flux, dancing in the air, reacting with sunlight and oxygen, clinging to fabrics or being absorbed into skin. Some evaporate in seconds, others linger for hours, but none last forever. In food, scent is a critical component of flavour. Much of what we think we taste is actually smell. When you chew food, volatile compounds are released into your mouth and travel up to your nasal cavity through a process called retronasal olfaction. It's why your sense of taste is so dull when you have a cold. Those flavour molecules can't reach the receptors that interpret them. Cooking dramatically changes a food's aroma profile by triggering the Maillard reaction and other chemical processes. A raw onion smells sharp and sulphurous because of sulphur-containing compounds. When sautéed, those molecules are broken down and replaced with sweeter, nuttier aromas. The change in smell reflects a change in chemistry over time, often just minutes, but enough to transform something eye-watering into something mouth-watering. Smell also plays a role in how we experience aging in objects and spaces. Old books develop a distinctive scent from the breakdown of cellulose and lignin in the paper, releasing compounds like vanillin and benzaldehyde. Antique furniture, leather jackets, even houses can all develop what we call a smell of age, a gentle symphony of slowly changing organic compounds. Interestingly, some modern perfumers and chemists try to capture the smell of nostalgia itself. Scents like New Baby, Old Library, or The Beach in Summer are recreated using complex blends of molecules meant to mimic real-life experiences. These synthetic compositions aren't just artistic, they're scientific experiments in emotional chemistry, trying to evoke a time, place, or feeling using molecules alone. Yet despite all our attempts to bottle or preserve scent, time eventually wins. Volatile compounds are, by definition, meant to evaporate. The very thing that makes them capable of being smelled also ensures their eventual disappearance. That perfume you love will eventually fade. The bouquet of fresh flowers will lose its magic. The memory of a kitchen filled with the scent of cinnamon rolls will outlast the aroma itself. And that's part of what makes smell so precious. It is fleeting. It is ungraspable. You can't freeze a smell in the way you can a photograph or a song. You can recreate it, but you can't hold on to it. It arrives, delights, and disappears. And in that brief moment, it connects you to a world full of chemistry, memory, and meaning. So breathe deeply. Catch the scent of a rose in bloom, a candle just blown out, or the first breeze after a summer rain. These are moments carved in molecules, drifting past on invisible currents, telling stories that only the nose can hear, and only for a little while. In the quiet corners of the forest, where fallen leaves curl into soft carpets and tree trunks slump into the soil, a slow and essential process is always unfolding. This is the language of decay in nature, a kind of whispered conversation between time and matter, where everything that once lived begins its return journey. While decay might seem like an ending, in the natural world it's more like punctuation, sometimes a full stop, sometimes a gentle comma before something new begins. At the centre of this cycle is compost, the unsung hero of ecosystems. Composting is nature's recycling system, a grand collaboration between bacteria, fungi, invertebrates, and time. Organic material like dead leaves, food scraps, and wood shavings are gradually broken down into a rich, dark substance called humus. Not to be confused with a chickpea-based snack, humus is the final, stable product of decomposition. It's what gives fertile soil its earthy smell and remarkable ability to hold water and nutrients. The process begins almost immediately after something organic dies, microbes moving quickly, using enzymes to dismantle complex molecules into simpler ones. Carbohydrates, proteins, fats all get taken apart piece by piece. Larger decomposers like earthworms, beetles, and millipedes join in, shredding and mixing the material as they eat and excrete. This isn't chaos, it's chemistry with a purpose. Each organism plays a role, breaking down matter into forms usable by plants and other life. Temperature is a key player in the composting process. As microbes metabolize the material, they release heat. In a well-managed compost pile, the temperature can rise to 60 or even 70 degrees Celsius, creating a hotbed of microbial activity. This heat helps destroy pathogens and weed seeds, making the final product safer for gardens and farms. Eventually, the temperature drops, the compost cools, and a more stable community of microbes takes over to finish the job. What emerges from all this decay is far from waste. Compost improves soil structure, increases biodiversity, and reduces erosion. It's teeming with microbial life, including beneficial bacteria and fungi that help plants grow. In this way, what dies is not gone, it's transformed. A banana peel becomes basil. A fallen leaf becomes the fern that grows beside it. It's not just recycling, it's reinvention. In forest ecosystems, this recycling is taken to a whole new level. Dead trees, fallen branches, and thick layers of leaf litter may look like debris, but they are vital parts of the forest's metabolism. These materials store nutrients, provide habitats for insects and fungi, and slowly release carbon and minerals back into the soil. A single rotting log can support hundreds of species, from woodlice to mosses to salamanders. And then there are the mushrooms. Fungi are the quiet custodians of decay, threading through soil and wood with delicate networks called mycelium. This mycelium acts like a digestive system outside the body, secreting enzymes that break down tough compounds like lignin and cellulose, the very molecules that make wood rigid and plants fibrous. Without fungi, forests would be buried in their own fallen leaves, unable to grow anew. Mushrooms themselves are just the fruiting bodies, the reproductive tips, of these vast underground webs. When the conditions are right, the mycelium sends up mushrooms to release spores, spreading the network further. Some fungi specialize in breaking down fresh plant matter. Others, called white rot and brown rot fungi, tackle the hardest jobs, decomposing dead trees and unlocking nutrients trapped in lignified cell walls. The pace of this work varies. A soft fruit or leafy green might decay in days, a sturdy branch could take months or years, a tree trunk might take decades to fully return to the soil. But this timeline is important. It creates layers of decay, supporting a constantly shifting community of organisms. Early colonizers pave the way for later arrivals. Each phase of decay creates opportunities for new life. The journey from leaf to loam is a slow choreography of chemical changes. As plant material breaks down, carbon is released as carbon dioxide. Nitrogen is converted into forms that plants can absorb. Minerals like potassium, phosphorus, and calcium are freed from their organic cages. Even the pigments in leaves, chlorophyll, carotenoids, anthocyanins, are dismantled, their molecules recycled or absorbed into new life. This chemical turnover is critical for maintaining healthy ecosystems. Without decay, nutrients would remain locked in dead matter, unavailable for new growth. The soil would grow poorer with each generation of plants. In this way, decay is not the opposite of growth, it is its foundation. Insects play a surprisingly large role in this cycle. Dung beetles, carrion flies, termites, and countless others are nature's cleanup crew. They feed on decay, transport nutrients, and aerate the soil. Even the smellier aspects of decomposition serve a purpose. Those potent odours help attract the very insects and microbes needed to continue the process. What we wrinkle our noses at is, for many organisms, the scent of opportunity. Decay is also deeply seasonal. In temperate forests, autumn brings a cascade of leaves to the forest floor, a banquet for decomposers. In winter, microbial activity slows and decay hits pause. When spring returns, so does the heat, and with it, a burst of renewed decomposition. This seasonal rhythm ensures that decay doesn't overwhelm the system all at once. It spaces out the return of nutrients, matching the growth cycles of plants. Some environments take decomposition to creative extremes. In peat bogs, for instance, the low oxygen, high acidity, and cool temperatures dramatically slow microbial activity. Organic material can remain preserved for thousands of years. Entire human bodies have been found in bogs, astonishingly intact, with skin, hair, and even clothing surviving the centuries. In these places, time moves differently. Decay whispers instead of shouts. Deserts present the opposite challenge. With very little moisture, decomposition slows due to a lack of microbial activity. Plant material may become brittle and weathered, but not truly broken down. Bones can bleach in the sun for years. Decay depends on a careful balance of conditions. Without water, microbes sleep. Without warmth, they shiver. Without oxygen, they shift strategies. The process never stops completely, but its tempo changes dramatically. Even the oceans have their own language of decay. When a whale dies and sinks to the seafloor, it creates a whale fall, a sudden abundance of nutrients in the deep sea. Scavengers rush in first. Sharks, eels, and crabs strip away the flesh. Then microbes, worms, and other decomposers get to work, slowly reducing the skeleton and enriching the surrounding sediment. This process can take decades, and in the deep sea, where food is scarce, it sustains entire ecosystems. Decay is not always beautiful, at least by our usual standards. It smells, it seeps, it attracts the kind of attention we typically avoid. But look closely, and it reveals an elegant system of transformation, a way for the old to make room for the new, a process not of loss, but of change. It's not the end of the story, it's just a quieter chapter. Nature has no waste. In the grand ledger of ecosystems, everything is reused. Molecules travel in loops, not lines. What was once a tree may become a fern, then a bird, then a feather, then a speck of soil. In that journey, decay plays a vital role. Always taking, always giving, never idle. So the next time you walk through the woods and see a rotting log, or notice fallen leaves turning to mulch, try not to think of it as something ending. Think of it as a sentence mid-phrase, a story continuing underground, molecule by molecule. Because in nature, decay isn't tragic, it's the soil's way of speaking, quietly promising that everything we see will one day nourish something else. Some stories are written in ink, some carved in stone, and some are told by molecules so ancient and quiet they almost escaped notice. But chemical fossils, as subtle as they may be, are among the most powerful storytellers of Earth's deep past. These are the remnants of ancient biochemistry, locked in rock, amber or oil, waiting patiently for millions of years until someone with a good microscope and a curious mind comes along to listen. Unlike bones or shells, which are physical fossils you can hold and admire, chemical fossils, also called molecular fossils or biomarkers, are invisible to the naked eye. They're the molecular traces left behind by long-gone organisms, fragments of lipids, pigments, waxes and other durable compounds that manage to resist the slow grind of decay and geologic transformation. While soft tissues usually decompose quickly, certain molecular components are surprisingly resilient. And in just the right conditions, low oxygen, stable temperature, rapid burial, they become tiny time capsules. Take, for example, hopanoids. These are lipid molecules produced by bacteria, and some forms are known to persist in sediment for billions of years. When paleobiologists detect hopanoids in ancient rock, they can infer that bacteria were present at that time, even if no visible fossil remains exist. In essence, we're reading the chemical signature of life, long after the life itself has vanished. It's molecular ghost hunting, but with a mass spectrometer instead of a flashlight. Another superstar in the world of chemical fossils is porphyrin. This ring-shaped molecule is a relative of chlorophyll and hemoglobin, meaning it played a central role in photosynthesis and oxygen transport. Traces of degraded porphyrins have been found in ancient shale, revealing that photosynthetic organisms were thriving hundreds of millions of years ago. Their molecular descendants are still around, catching sunlight and releasing oxygen, but the original compounds have faded into whispering echoes. Sometimes these chemical fossils are stunningly direct. In fossilized leaves, scientists have detected remnants of the original plant's waxy coating, cutin and suberin, that protected it from drying out. In ancient bones, residual collagen fragments have been preserved under just the right mineral conditions. Even pigments like melanin have been found in fossilized feathers and skin, allowing researchers to make educated guesses about the colors of extinct animals. Yes, some dinosaurs were likely more dapper than we imagined. And then there's amber, the golden time machine. Formed from the fossilized resin of ancient trees, amber is a master of preservation. It can encapsulate entire insects, plant fragments, even air bubbles from prehistoric atmospheres. But beyond its visible contents, amber also traps molecular traces. Proteins, DNA fragments, and even scent compounds have been found in amber specimens millions of years old. These molecules provide clues about the diets, microbiomes, and environments of ancient life forms, like nature's own field notes written in resin. Reading these molecular relics isn't easy. It requires sensitive techniques like gas chromatography and mass spectrometry, which allow scientists to separate and identify the molecular components of a sample. Sometimes the molecules are slightly altered, transformed by heat, pressure, or chemical reactions over time. But even degraded, they retain enough of their original structure to tell us something meaningful. It's a bit like reading a letter where the ink is smudged. You may not get every word, but you can still grasp the message. Chemical fossils have reshaped our understanding of life's early history. For a long time, scientists believed that complex life exploded onto the scene during the Cambrian period, about 540 million years ago. But molecular evidence from rocks even older than that, dating back over 2 billion years, shows that microbial life had already established complex ecosystems in shallow seas. Steraneas, which are molecular fingerprints of eukaryotic cells, appear in these rocks, suggesting that the ancestors of plants, fungi, and animals were quietly evolving long before their skeletons made it into the fossil record. This is the power of chemical storytelling. It can fill in the blanks left by broken bones and vanished bodies. It gives voice to organisms that were too small, too soft, or too subtle to leave traditional fossils. And it connects the biology of today to the geochemistry of yesterday in a direct molecular line. Of course, not all chemical fossils are quietly hiding in stone. Some are bubbling up from the ground, quite literally. Fossil fuels, coal, oil, and natural gas, are perhaps the most famous and misunderstood of all ancient molecular artifacts. Formed from the compressed remains of long-dead plants, plankton, and marine microbes, these carbon-rich substances are time capsules of ancient sunlight. Every molecule of oil was once part of a living organism, photosynthesizing energy from the sun and capturing it in chemical bonds. Over millions of years, that organic material was buried under sediment, subjected to heat and pressure, and transformed into hydrocarbons. When we extract and burn fossil fuels, we're releasing that stored energy, ancient solar power, captured by algae and ferns and now used to drive cars, power factories and heat homes. It's a strange legacy, using the breath of ancient plankton to toast your morning bagel. But this release comes at a cost. Burning fossil fuels not only liberates energy, but also releases carbon dioxide, a greenhouse gas. The carbon that was safely tucked away underground for geological epochs is now rejoining the atmosphere, altering the balance of Earth's climate. In this sense, chemical fossils are not just historical artifacts, they're active participants in our present and future. Our deepening understanding of these ancient reactions has also inspired new ideas. Scientists are studying the chemistry of fossil formation to better understand how to preserve modern biological samples, create synthetic fuels, or mimic natural processes for carbon storage. By examining how time and pressure transform organic matter, we gain insights into how to manage Earth's resources more wisely. Chemical fossils also invite us to think about time differently. Unlike a calendar or a clock, they don't mark hours or days. They record conditions, temperature, pressure, redox environments, biological presence, across millions of years. They're the scribes of deep time, writing not in symbols but in carbon chains, methyl groups and stable isotopes. Imagine being able to read a piece of shale the way you read a diary. You might learn that a shallow sea once teemed with plankton, that oxygen levels were low, that a bloom of bacteria left behind a waxy molecular trace. You'd see the ancient Earth not as a static canvas, but as a living, breathing, chemically expressive world, with every layer of rock holding a memory. These stories are everywhere, in tar pits, peat bogs, lake sediments, even in the layers of grime on ancient pottery. Archaeologists often analyse food residues left on pottery shards. discovering what people cooked, traded or fermented thousands of years ago. Lipids from milk, fats from meat, residues from wine or oil. These are all forms of molecular memory, helping us reconstruct human history one molecule at a time. Chemical fossils are also helping in the search for life beyond Earth. When rovers explore Mars or scientists analyse meteorites, they look for biomarkers, molecules that might suggest the past or present existence of life. Even if we don't find bones or footprints, a specific pattern of organic molecules could be enough to suggest biology once bloomed on another planet. It's an exciting frontier where chemistry and imagination meet. So the next time you hold a fossil, consider that what you're seeing is just part of the story. Beneath the visible surface, at the molecular level, there may be more. Fragments of ancient lipids, hints of pigments, echoes of photosynthesis. These molecules have travelled through unimaginable stretches of time to reach us, carrying whispers from oceans long gone, forests long buried, and microbes whose only legacy is a molecule in stone. In the great theatre of Earth's history, chemical fossils are the background music, quiet, persistent, and utterly essential. They remind us that even when life seems gone, something always remains. A trace, a signature, a molecule waiting to be read. Memory feels like magic. One moment, you're quietly sipping tea, and the next, the scent of jasmine or the clink of the spoon triggers a vivid image of a garden from years ago. A place, a voice, a detail you'd forgotten you remembered. But underneath the wonder lies chemistry, rich, dynamic, and always in motion. Memories aren't just stored like files on a hard drive. They're built, maintained, and reshaped by proteins, ions, and molecules dancing in the synapses of your brain. And just like everything else touched by time, memory changes. Some parts fade, others deepen, and some simply vanish. At its foundation, memory is a physical process. Your brain, made up of billions of neurons, stores experiences as changes in connections between cells. Each time you learn something new, whether it's a language, a melody, or just where you left your keys, a network of neurons subtly rewires itself. These changes happen at the synapses, the tiny gaps between neurons where electrical signals are converted into chemical ones. When a neuron is activated, it sends an electrical impulse down its axon. At the synapse, that impulse triggers the release of neurotransmitters, chemical messengers like glutamate, dopamine, or acetylcholine. These chemicals cross the gap and bind to receptors on the next neuron, continuing the signal. But if that particular connection is used repeatedly, it becomes stronger. The brain responds by growing more receptors, building up supporting proteins, or even increasing the size of the synapse itself. This is known as synaptic plasticity, and it's the molecular foundation of learning and memory. The most well-known form of this plasticity is called long-term potentiation, or LTP. It's a long-lasting increase in signal transmission between two neurons that have been activated together repeatedly. LTP involves a cascade of biochemical events. Calcium ions enter the cell, enzymes are activated, gene expression changes, and new proteins are synthesized. Over time, this leads to the physical strengthening of a synaptic connection. Your memory of your best friend's birthday, your first day at school, or your bicycle route home, all of these depend on synaptic strength shaped by LTP. Proteins play a central role in this process. Some proteins help neurons grow and stabilize their connections. Others act as signaling molecules, keeping the communication lines open, or dampening them when needed. Many of these proteins have lifespans that range from hours to days, which means memory isn't static. It's maintained by continuous protein turnover. Just like your skin cells or muscle tissue, the molecular scaffolding of memory is constantly being broken down and rebuilt. This brings us to a fascinating tension in the chemistry of the brain. How can something as fleeting as a protein support something as durable as a lifelong memory? One theory suggests that memory is preserved through feedback loops. Once a connection is strengthened, it encourages the continued production of the proteins that sustain it. Another possibility is that memory becomes encoded in structural changes, alterations to the physical layout of synapses, or even entire neural circuits that remain even as individual molecules come and go. But not all memories are built to last. Some fade quickly, not because they weren't important, but because they weren't reinforced. This process, known as synaptic pruning or memory decay, is also chemically driven. When a memory isn't used or recalled, the associated synapses weaken. Proteins are not replenished, receptors are removed, and the connection gradually dissolves. It's a bit like a path in the woods. Walked often, it stays clear. Neglected, it grows over with time. On a molecular level, forgetting involves enzymes like protein phosphatases, which remove phosphate groups from key proteins, involved in maintaining synaptic strength. This reversal undoes the changes made during learning, gently dimming the brightness of old experiences. Forgetting isn't always a flaw, it's often adaptive. It helps us focus, update outdated information, and avoid mental clutter. In a world where we encounter endless data each day, forgetting helps us remember what matters. Still, some memories persist with remarkable clarity. Emotional memories, for example, tend to stick. That's because strong emotions trigger the release of stress hormones like cortisol and adrenaline, which influence brain regions like the amygdala and hippocampus. These hormones can enhance the formation and consolidation of memory by affecting gene expression and protein synthesis. It's part of why you remember that time you got lost in a strange city more vividly than what you had for lunch last Wednesday. Yet as we age, the chemistry of memory becomes more complex. The efficiency of neurotransmission can decline, protein synthesis may slow, and oxidative stress can damage neurons. Calcium regulation, so essential for signaling, becomes less precise. Some synapses weaken, and others may fail to maintain their structure. While this doesn't always result in dramatic memory loss, it can lead to what many call senior moments, those brief lapses in recall or slower processing that most people experience with age. In some cases, the molecular wear and tear becomes more severe, leading to neurodegenerative diseases like Alzheimer's. Alzheimer's is characterized by the accumulation of two main types of molecular debris: amyloid beta plaques and tau tangles. Amyloid beta is a peptide that aggregates outside neurons, forming sticky clumps that disrupt communication. Tau is a protein that, when misfolded, forms twisted fibers inside neurons, interfering with internal transport systems. These aggregates are toxic. They trigger inflammation, oxidative damage, and cell death. As neurons degenerate, connections are lost, and the structural network that holds memories begins to unravel. The hippocampus, crucial for forming new memories, is often one of the first regions affected. People may struggle to form new memories, recall names, or navigate familiar environments, not because they've forgotten in the usual sense, but because the molecular infrastructure of memory is breaking down. Despite this sobering reality, researchers are making strides in understanding and addressing the molecular basis of memory disorders. Investigational treatments aim to prevent protein aggregation, enhance synaptic plasticity, or reduce inflammation. Some studies are exploring how sleep, exercise, and diet influence the biochemistry of memory. For instance, sleep plays a vital role in memory consolidation. During deep sleep, the brain replays patterns of neural activity, strengthening connections formed during the day. This rehearsal is thought to help embed experiences into long-term memory. Diet, too, may shape memory on a molecular level. Antioxidants from fruits and vegetables, omega-3 fatty acids from fish, and compounds like flavonoids have been shown to support synaptic health and reduce oxidative stress. Even the act of learning itself promotes brain plasticity. Mental challenges, curiosity, and new experiences stimulate the production of brain-derived neurotrophic factor, a protein that supports neuron survival and growth. So while memory can be fragile, it is also astonishingly adaptable. The chemistry behind it is in constant flux, writing, revising, deleting, and editing. Every time you recall a memory, you slightly alter it, updating the proteins and connections involved. Memory isn't just a file, it's a living process, and with each recall, you're not just retrieving information, you're re-experiencing it, chemically and emotionally. In this way, memory is time captured and reshaped. It's your life rendered in molecules, stored not in ink or stone, but in ions, neurotransmitters, and proteins. Forgetting, too, is part of this dance. It allows room for new memories, for change, for letting go. And within that balance of remembering and forgetting, of building and releasing, we find the chemistry of being human, a brain sculpted by time, writing itself, one molecule at a time. Entropy has a bit of a reputation. The very word tends to conjure images of messes, crumbling systems, or an overly dramatic physics teacher warning you about the impending heat death of the universe. But beneath all the ominous-sounding language, entropy is really just nature's quiet preference for disorder. It's not malicious or tragic. It's not even inherently bad. It's just the way the universe leans, molecule by molecule, towards spreading things out. So what exactly is entropy? In its simplest sense, entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged. The more possible configurations, the higher the entropy. A neat stack of playing cards has low entropy because it's highly ordered, and there's only one way to arrange it that way. Shuffle the deck, and the number of possible arrangements explodes. Each new order is just as likely as the last, and suddenly, you've increased the entropy without even trying. In chemistry and thermodynamics, entropy tells us about energy distribution. Energy naturally spreads out over time if given the chance. Hot things cool down, gases expand, and highly ordered systems tend to become less organised unless work is done to maintain them. This tendency isn't a flaw in the system, it is the system. At a molecular level, everything is vibrating, rotating, bouncing, and colliding. Molecules don't stand still, they're constantly seeking new configurations, distributing energy among themselves in countless ways. A gas in a container, for instance, doesn't gather in one corner. Its particles move around freely, exploring the space, maximizing their entropy. The probability of all gas particles huddling together on one side of the room is astronomically low, not because they can't, but because the number of other arrangements is vastly, overwhelmingly larger. Entropy is also a great friend of time. In fact, the arrow of time, the one-way direction from past to future, is tied directly to the increase of entropy. In our everyday experience, we see time as flowing forward. Eggs crack, but don't uncrack. Ice melts, but puddles don't spontaneously form into cubes. These changes reflect an increase in entropy. The future, it turns out, is the direction in which disorder grows. This isn't a law built on intuition, it's one of the central principles of thermodynamics. Specifically, the second law of thermodynamics states that in an isolated system, entropy never decreases. Systems will evolve toward the state with the highest number of microstates, or internal arrangements. Left alone, things don't stay tidy. They fall apart, diffuse, and spread their energy thin. This doesn't mean everything dissolves into chaos instantly. Entropy doesn't erase structure. It just makes structure less likely to persist without effort. Living systems, for example, appear to defy entropy by maintaining complex order. Think of us tree-growing leaves, a brain storing memories, or a crystal forming in a solution. But these systems are not isolated. They exchange energy with their environment. The entropy of the whole, organism plus surrounding, still increases overall. Life maintains order locally by creating disorder elsewhere, often by releasing heat or waste. Even our own bodies are engines of entropy management. We eat food, breaking down complex molecules into simpler ones. That release of energy fuels processes that build and maintain our cells, but it also produces heat, carbon dioxide, and other byproducts, tiny packages of entropy sent back into the world. Every breath you exhale carries with it water vapor and carbon dioxide that contribute to the universe's gradual lean toward disorder. Entropy also plays a starring role in chemical reactions. Whether or not a reaction will occur spontaneously depends not just on energy changes, but also on changes in entropy. Some reactions absorb energy but still proceed because they result in a significant increase in disorder. For example, dissolving salt in water takes energy, but it also dramatically increases entropy as the ordered crystal lattice breaks apart and ions spread out into the liquid. From a molecular perspective, many of the changes we associate with decay, rust forming on iron, fruit rotting on the counter, candles melting into wax puddles, are physical manifestations of entropy at work. Over time, complex structures break down into simpler, more probable states. The specific path each reaction takes is governed by kinetics and energy, but the general direction toward more possible arrangements is always the same. Entropy is even lurking in your cup of tea. When you add milk to hot tea, the milk doesn't stay in a little cloud. It disperses, spreading its molecules throughout the liquid. That blending increases entropy. Once mixed, you can't unmix it by waiting. Time pushes the system forward, not backward, and entropy is the molecular signature of that push. In the grandest sense, entropy tells us about the fate of the universe. Our cosmos began in a state of low entropy, a hot, dense and relatively uniform soup of particles. Over billions of years, gravity pulled matter into stars, galaxies and planets. But overall, entropy has increased. Energy has spread out. Stars burn fuel and release heat. Systems evolve, radiate, and decay. Eventually, in the far distant future, entropy will reach a point where no more useful energy is available to do work. This hypothetical state is sometimes called heat death, a rather dramatic name for a universe in thermodynamic equilibrium where everything is as spread out and evenly distributed as it can possibly be. But we are nowhere near that end. In the meantime, entropy allows all sorts of fascinating things to occur. It enables diffusion, mixing, and the spontaneous formation of patterns. It allows stars to shine, engines to run, and ice cream to melt just enough to be scoopable. Without entropy, time might stand still. Molecules wouldn't move and nothing new would ever happen. And it's not all doom and dust. Entropy isn't out to destroy structure, it simply favours probability. A messy bedroom isn't inherently worse than a tidy one, it just has more ways to be messy than clean. If your sock drawer is always in disarray, blame entropy, and perhaps your own habits. But at the molecular level, that drawer full of jumbled socks is a microcosm of the universe's fondness for options. It's this probabilistic nature that makes entropy so captivating. It doesn't demand chaos, it simply tilts the odds. Molecules have more ways to be disordered than ordered, and over time, systems drift toward those higher probability states. The math backs it up. The entropy of a system is related to the logarithm of the number of microstates. So even a small increase in complexity leads to a huge increase in entropy. Entropy also brings with it a certain peace. It reminds us that change is natural, that structures wear down not out of failure but out of participation, that even in breakdown there is beauty, a fallen leaf, a melting glacier, a cooling ember, all a part of the same quiet tendency of the universe to explore its possibilities. And remarkably, within that entropic push toward disorder, tiny pockets of temporary order still emerge. Galaxies, cells, crystals, consciousness. We are not separate from entropy. We are improbable arrangements that arose in defiance of it, only to ultimately return and contribute to the spreading web of possibility ourselves. So don't be afraid of entropy. It's not a villain. It's the universe's way of moving forward. It's the music of time made audible in chemistry, the murmur of change in every molecule. It's the soft, inevitable tug that turns ice into water, buildings into ruins and memories into dreams, In the end, entropy is time's signature, not etched in clocks but whispered in molecules as they explore all the ways they can be. Time travel has always been one of humanity's favourite thought experiments. Who hasn't dreamed of rewinding a moment, undoing a mistake, or reliving a perfect day? In science fiction, time machines were spark and fling protagonists through centuries. But in the real world, particularly in chemistry, time travel doesn't quite come with blinking lights or dramatic sound effects. Instead, it shows up in subtler forms, reversible reactions, dynamic equilibrium, and the occasional illusion of undoing change. At the molecular level, the question becomes not, can we travel through time, but rather, can we coax a molecule to unreact, to step backwards, even briefly, before moving forward again? Let's begin with the idea of reversible reactions. Unlike the ticking of a clock or the browning of a banana, not every chemical change is one way. In fact, many reactions in nature are perfectly capable of going forward and backward, depending on the circumstances. These are known as reversible reactions, and they are the molecular equivalent of a conversation rather than a proclamation. Reactants form products, and under the right conditions, those products can turn back into reactants. It's a chemical give and take. Consider the classic example of carbon dioxide dissolving in water to form carbonic acid. CO2 reacts with water to create H2CO3, but this reaction is in delicate balance. If the conditions change, say, if you open a bottle of soda and let the gas escape, the carbonic acid quickly shifts back into carbon dioxide and water. This equilibrium allows the system to respond dynamically to changes, maintaining a kind of molecular conversation with the environment. At the heart of reversible reactions is the concept of chemical equilibrium. This doesn't mean everything stops. It means the forward and reverse reactions occur at the same rate. Molecules are still changing, colliding and transforming, but the overall concentrations remain constant. It's like a busy intersection where cars are entering and exiting at equal speeds. You might not notice the motion unless you look closely, but it's happening all the time. Equilibrium gives us a taste of chemical time travel. In a sense, molecules are flipping back and forth between states, exploring possibilities, and settling into patterns that reflect their environment. This is especially common in biological systems, where enzymes facilitate reactions that are easily reversible. Your own body uses these principles constantly. Glucose, for instance, can be stored as glycogen or broken back down, depending on energy needs. Chemical equilibrium allows your metabolism to adapt, responding not to the past but to the present moment with options ready in both directions. However, not all reactions are this forgiving. Many are essentially irreversible under normal conditions. Burning paper, for instance, produces gases and ash that will never spontaneously reassemble into a notebook. The energy has been released, the bonds permanently rearranged, and entropy has done its work. Even though atoms themselves are conserved, their arrangement, what made them useful or recognizable, is not. This is time's arrow in action, the natural statistical tendency of systems to move from order to disorder, from usable energy to entropy. Despite this, humans have long dreamed of slowing, stopping, or even reversing the ravages of time at the molecular level. This is where the world of anti-aging comes in, often with promises as shiny as a freshly polished apple. Many of these ideas orbit around a common culprit: oxidative stress. This refers to the damage caused by reactive oxygen species, molecules that are byproducts of normal metabolism but can harm DNA, proteins and lipids if not properly managed. Enter antioxidants. These are compounds that can neutralize reactive oxygen species, preventing or reducing cellular damage. In theory, they act like molecular shields, donating electrons to stabilize dangerous radicals without becoming reactive themselves. Vitamin C, vitamin E, and compounds like glutathione or flavonoids in fruits all serve as antioxidants. They help maintain cellular health, reduce inflammation, and support normal aging processes. But while antioxidants are chemically helpful, they are not time machines. No amount of blueberries or green tea can reverse aging or stop time in its tracks. Once a protein is damaged or a strand of DNA is mutated, the body must either repair or replace it. Antioxidants can reduce the rate of damage, but they can't undo changes that have already occurred. The idea of erasing wrinkles at the molecular level is more poetic than practical. Some anti-aging products and supplements go a step further, invoking the idea of telomeres, the protective caps at the ends of chromosomes that shorten with each cell division. It's true that telomere length is linked to cellular aging, and some compounds claim to preserve or lengthen them. But while the chemistry behind telomeres is fascinating, it's also incredibly complex. Simply adding a compound to a test tube, or your morning smoothie, doesn't grant you molecular immortality. In fact, artificially lengthening telomeres without regulation can lead to uncontrolled cell growth, better known as cancer. And then there's the broader question: can we stop time in a test tube? Can a chemical system be placed in suspended animation, frozen not just in temperature but in reactivity? To a limited extent, yes. Cooling a reaction to extremely low temperatures can slow it down dramatically. In cryogenics, for example, biological samples are preserved by halting metabolic activity at the molecular level. Enzymes stop working, membranes stiffen, and chemical reactions stall. But this isn't true reversal. It's more like pressing pause on a very slow DVD. When you press play again, the story continues from where it left off. Scientists can also trap reactive intermediates, unstable molecules that exist briefly during a reaction, using spectroscopy or rapid freezing techniques. These glimpses into transition states offer insights into how reactions proceed and, occasionally, how they might be redirected. But again, we're observing moments in time, not reversing them. Even in highly reversible systems, there are limits. Energy input is often required to drive a reaction backward. Reassembling broken molecules isn't spontaneous. It's uphill, energetically speaking. In biochemical systems, this energy typically comes from molecules like ATP, which acts like a molecular battery. Without energy, chemistry tends toward randomness, not reconstruction. Still, the dream persists. Could we one day rewind cellular aging? Could we erase chemical scars? Could we use nanotechnology to edit damaged molecules back into their original forms, one atom at a time? Perhaps. Research into protein refolding, molecular repair, and gene editing continues to push the boundaries of what's possible. But even the most advanced technologies will still work within the laws of thermodynamics. There will always be costs. Reversal is never free, and perhaps that's part of the charm. Time, even at the molecular level, flows forward more often than not. Reactions happen. Change accumulates. The dance of molecules writes the story of who we are, from how we heal, to how we age, to how we remember. Chemistry doesn't stop time, but it gives us exquisite detail on how time feels to a molecule, as balance, as motion, as transformation. In the end, chemical time travel isn't about rebuilding the past. It's about understanding the rhythm of change. Some reactions can be nudged backward. Others move only one way. But all of them reveal something about the nature of time. Not as a ticking clock, but as a dynamic flow of rearrangement and possibility. So while we may never rewind our lives like a tape, we can take comfort in the idea that, at the molecular level, time is full of options, loops, pauses, reversals, and new beginnings. It's not about conquering time, but learning to move with it, one reaction at a time. Everything in the end changes. Slowly, quietly, and often invisibly, the molecules around us are rearranging themselves. A crust of toast goes stale. A star drifts into silence. A scent drifts off a page of an old book and is gone forever. But this isn't a story of loss. It's a story of transformation. one that unfolds over minutes, months, millennia. The molecules in your body, your chair, your coffee mug, and even the air around you are constantly shifting. They collide, break apart, form new bonds, and dance to the rhythm of time's chemistry. Rust creeps, leaves decay, proteins fold and forget. But through all of it, there's a kind of gentle poetry in how change happens. Nothing is frozen, nothing stays. And somehow, that's what makes it all so beautiful. The chemistry of time doesn't happen with a bang. It's not fireworks or explosions, not usually. It's the softening of a fruit, the dimming of a fragrance, the way a glacier melts drop by drop. It's slow magic, a spell that turns the world not into chaos but into something continuously new. Every reaction we've explored, every rusting beam, every browning banana, every drifting molecule of perfume has whispered something about impermanence, and not as a threat, but as a comfort, because nothing being permanent also means that nothing is stuck. Staleness gives way to fresh breath. Dead leaves feed new roots. Even memory, as fragile as it is, leaves a molecular trail, a quiet echo in proteins and pathways. It turns out that time is less like a thief and more like an artist. It paints slowly, sometimes erasing, sometimes layering, but always working with care. Every faded colour, every wrinkled surface, every aging molecule tells a deeper story, not of decay, but of becoming. And perhaps that's the secret to why time makes life beautiful. If everything were frozen, if bananas never browned, if perfumes never faded, if memories never softened around the edges, we'd lose the contrast that gives life its richness. It's precisely because things change that we notice them at all. A flower smells sweeter when we know it won't last. A shared meal feels warmer when we realize it's part of a fleeting moment. Even in the deepest, most stable molecules, crystals frozen in amber, carbon trapped in ancient rock, we find the imprint of time, and even they eventually will move, react, transform. There's no such thing as truly permanent, just very, very patient. In the end, we are part of this too. Our bodies, our thoughts, our breath. They're all expressions of chemical change. The same atoms that flickered in the cores of ancient stars now swirl in your cells. The same processes that rot an apple also help neurons speak. And when we go, when our molecules loosen their bonds and return to the broader pattern, they will not vanish. They'll continue to participate, to transform, to move with time. So wherever you are, at whatever hour you're listening, I hope you found a little calm in all of this chemistry. Perhaps it's late. Perhaps the day is just beginning. Maybe you're lying in bed, letting the molecules in your muscles slow, your breathing soften. Maybe you're still wide awake, your neurons firing through this curious wander through the nature of time. And just as we began, let me ask you once more, where are you watching from? What time is it there? What is the shape of your moment? What air is brushing your skin right now? Because even as this video ends, your molecules, your world, continue to shift in their slow, intricate patterns. You're part of that motion, part of that chemistry, part of that quiet poetry. If this journey brought you a sense of wonder, or perhaps a little peace, I'd be grateful if you gently pressed that like button, maybe even subscribed, and shared where you're watching from in the comments. Not just for me, but to leave your mark, however small, in the drifting molecules of this shared space. Carry you forward, one molecule at a time.